Greetings from the New York City College of Technology. My name is Spherical, and welcome to lecture number 5 of Physics 2. So today we're talking about optics. Ooh, this chalk is smooth. Okay, so what does optics mean? Well, optics is essentially the study of how light or electromagnetic radiation acts when it hits and goes through surfaces. So there were 3 main actions in optics. Today we'll be talking about 2 of them, reflection and refraction. First up, we've got reflection. So reflection just follows a very simple law. Theta I equals theta R. You have a plane mirror and anything over here gets completely reflected. Probably have a mirror like this in your dressing room or somewhere else. So a flat mirror like this with an object on the ground, well, let's see what happens when we look inside the mirror. If we have, if we have an observer looking at this, let's draw the ray of light that goes towards their eyes. Let's think about this for a second, actually. So this will emanate a ray of light in exactly this direction in order to travel and hit this guy's eye. And the thing is, this guy is going to perceive the light as coming from all the way on the other side. We draw the ground and extend it over here. And this guy is going to perceive the light as being emitted by a mirage on the other side. So essentially, a mirror image is created. And you can recreate the same effect if you take the light from this and bounce it so that it goes right into his eye. Then, if you trace the line right over here, it's going to go straight to the bottom. So, this shape that's produced on the other side is a mirror image. This effect can also be created with spherical mirrors, which appear as circular mirrors on a 2D space. So, essentially, all we got to do is, what are you doing? We take a circle, we take a little slice of our circle, and that is our mirror. This is what a concave mirror looks like. While if I were to go on the other side, this is what a convex mirror would look like. So, let's say we have an image right over here. Now, we want it to reflect right off into this guy's eye. Alright? So, here's what the mirror is going to do. If we emanate light straight this way, it's going to come right over here. Why? Because what it's doing is it's actually reflecting off a tangent line to the circle right over here. So, the normal to this tangent circle is actually way over here. It means it's not going to go this way. It's going to come right over in this direction. And here's a similar phenomenon. That means that at the end of the day, an observer will see a mirror image that's smaller and upside down on the other side of the ground. So that is how circular mirrors work, or spherical mirrors rather. So now we know what reflection is. Now let's talk about the other motion of light. We have light going from medium 1 to medium 2. So we've got light traveling in this direction. And here's the thing. It doesn't just continue in a straight line as it would if it was traveling through the same medium the whole time. Its path would actually be diverted. Just like so. Beautiful, right? Now, in actuality, it doesn't really look too much like this, but it's a combination of the two phenomena. A bit of the light gets reflected, while a bit of the light gets refracted. All right, so what does it mean to be refracted? Well, we can figure out the path of light being refracted using Snell's law. Essentially, take this, the boundary, and draw the normal line to the boundary exactly at the point where the light hits the boundary. Then all we need to do is measure this angle first and then this angle. So then we can formulate a relation. What? Between theta I and theta r. All we need to do is take the index of refraction of the initial, multiply it by sine theta 1. This turns out to be equal to the index of refraction of the second medium times sine of the reflected angle. Okay, so this is what we call Snell's law. Fuck you. Snell's law. Okay, so what is the index of refraction actually? Well, essentially, a simple way to describe it is just how friendly the substance is to the motion of light. So, if there are a bunch of molecules in the way which are preventing light from getting through, that would cause a high index of refraction. So, the index of refraction is essentially proportional, or inversely proportional actually, to the speed of light in a substance. So, in specific, N is C over V, where C is the speed of light in a vacuum, which is always 3 times 10 to the 8. So, 3 times 10 to the 8 meters per second squared, by the way, if you're curious. So, then we've got the friendliness of medium 1 times sine theta 1, sine theta I, is equal to the friendliness of medium 2 times sine theta r. Holy shit, your phone's getting more cracked by the day. Okay. So then, if you know this, and this, you can find theta r. Oh god, I just found r. Okay. So, for example, let's say we have air, which has a mean index of refraction of approximately 1, and water, which has an index of refraction 1.33. And then we have sine theta I is equal to 1.33 sine theta r. So 0.75 is equal to sine theta r over sine theta I. Yeah, okay. So this can cause several real-world phenomena, including desert mirages, which are caused very often in deserts. It's an optical illusion, which mostly comes from refraction and reflection, phenomena like these. And we also have the sparkling of a diamond. This also comes from the phenomena of reflection, especially total internal reflection.